Welcome to 5-Minute Papers on AI for the Planet. I'm Grace Lindsay. Our paper today is a Sentinel-3 foundation model for ocean color. Let's get started. It may seem like a simple question. What is the color of the ocean? But oceans display variations in surface color over time and space that can reveal a lot about the health of the marine ecosystems that lie beneath. For example, chlorophyll concentration controls how green the water is, and that color can be used as an indicator of phytoplankton activity. Phytoplankton convert inorganic carbon into organic matter, a process which forms the foundation of the marine food web, sustaining nearly all life in the ocean and generating a large portion of Earth's oxygen. In addition to reflecting healthy productivity, ocean color can also detect harmful algal blooms, which, if unchecked, can lead to a devastating loss of oxygen in the water. To help monitor ocean color, the Sentinel-3 satellite was designed with the Ocean and Land Color Instrument on board. This sensor measures energy at 21 different wavelengths, covering the optical and near-infrared regions of the electromagnetic spectrum. Scientists have devised numerous ways to use this color information to estimate chlorophyll concentrations and ecosystem productivity, but limited on-the-ground data makes it hard to identify these relationships in a robust and generalizable way. And that's where this paper comes in. In this paper, the authors build an ocean color foundation model based on color and temperature measurements from Sentinel-3. They then show how it can be fine-tuned to perform ecologically relevant downstream tasks. For pre-training, the authors start with a vision transformer architecture and train it via a masked autoencoder framework. In this framework, a few pixels in the input image are masked, and the goal of the model is to reconstruct those missing pixels. The reconstruction loss is calculated using the root mean squared error between the actual and predicted pixel values. The images used for this pre-training, the locations of which are shown here in blue, were selected to equally tile the different biogeographical regions of the ocean and were sampled from the years 2017 to 2021, resulting in nearly 500,000 observations. Model training on this data took approximately 12 hours, split across 4 GPUs. We can see how well the model performs based on the reconstruction loss for pre-training on this global map. The losses tend to be higher around the coastlines and in the mid-Atlantic. Inspection of the reconstruction shows that the model captures broad patterns but tends to be over-smooth compared to the data. Once pre-training is concluded, the model is fine-tuned on specific datasets to determine if the pre-trained weights capture transferable representations of ocean imagery that generalize well across downstream tasks. The green and pink points here show the locations of ocean-based measurements of chlorophyll concentration and of primary production, which is the rate at which carbon is being turned into organic matter. With only 103 on-the-ground observations for primary production and 188 for chlorophyll concentration, supervised fine-tuning on these datasets is very data-constrained, which makes it all the more important for the foundation model to learn rich and useful representations during pre-training. To perform this fine-tuning, a UNet-style fine-tuning head replaces the decoder that was used during pre-training, and the weights of this head are trained to generate chlorophyll concentrations or primary productivity estimates based on the Sentinel-3 images given as input. Looking at the foundation model's performance on predicting primary production, it shows a lower error rate than a transformer trained from scratch without pre-training, and than a much simpler random forest model. This suggests that the unsupervised pre-training has helped. To see an even larger benefit of pre-training, the authors look at how model performance on the primary production task changes as the amount of fine-tuning data increases. When the fine-tuning data is only a quarter of the size, the benefit of pre-training is even starker. Interestingly, the foundation model does not provide the same gains on the task of estimating chlorophyll concentration. Here, the pre-trained model works as well as a random forest model or a transformer without pre-training when looking at error rates. The authors, however, do provide evidence that the pre-trained model produces outputs that better capture the spatial structure of chlorophyll concentrations. To summarize, the authors develop a pre-trained foundation model for ocean color that can be adapted to downstream tasks. The model performs well despite limited availability of task-specific data, highlighting how foundation models can be leveraged to address critical planetary challenges that often suffer from data scarcity, particularly in low-resource regions. That's all for this episode. Remember to subscribe to this channel for more examples of how AI can be used to understand and protect our planet.